Hello guys, today we will be talking about sedimentation tank. Okay, the sedimentation tank is basically a tank that is used for the clarification of water, okay, by the process of sedimentation, and it can be affected by providing the conditions under which the suspended material present in water can settle out. So a storage reservoir may also serve as a sedimentation basin or a clarifier basin, but they cannot effect proper sedimentation because of the factors like the density currents, the turbulences caused by winds, and hence they cannot be relied upon. So special basins are therefore constructed in order to clarify the surface water or the reservoirs by the process of sedimentation. But three forces which control the settling tendencies of the particles, that is the two forces, the velocity of the flow and the shape and size of the particles. Okay, now the third force is the viscosity of the water or the temperature of water is left uncontrolled, as the same is not practically possible. So we have velocity of the water, we have the shape and size of the particles that are to be removed, and the viscosity of the water. Okay, now the size and shape of the particles can be altered by the addition of certain chemicals, like you can say coagulants like alum ferrichloride, and they make the sedimentation quite effective by leading to the settlement of even very fine particles here. However, their use is not made in a plain sedimentation tank. So we can say that there is a sedimentation tank and a sedimentation tank with the addition of coagulants or flocculants. Okay, now the sedimentation basins are generally made of reinforced concrete, and they can be rectangular or circular if we categorize them in the form of shape. And the long, narrow rectangular tanks with horizontal flow are generally preferred to the circular tanks with horizontal, radial, or spiral flow, or you can say peripheral flow. The capacity and the dimension of the tank should be properly designed so as to affect or impact a fairly high percentage of removal of the suspended material. A plain sedimentation tank under normal conditions may remove as much as 70% of the suspended, you can say suspended impurities in the water. Now this is my typical layout of the rectangular tank, or you can say a horizontal flow tank, where we have water coming. This is called influent. This is are the baffle walls. So baffle walls basically restrict the flow of the water. You can say they slow down the flow of the water so that there is an efficient or proper sedimentation of the particle or settling of the particles. This is my water level, and these are my sledge hoppers, and here the sledge settles down. This is my effluent line from where the water will be going out. So this is my typical layout of the horizontal flow tank. This is my typical layout of the circular sedimentation tank. Where you can see that we all again have an inlet, and then we have the outlet channel, and then also we have the weir and notches. Okay, basically they are going to measure the flow rate of the water, and then we have the sludge pipe and sludge sump also here to store the sludge, and sludge will be coming out here, and this is the discharge, and this is my influent well here, and this is my whole layout of the circular sedimentation tank, where the provide a central feed with a radial flow. Now in the design of the horizontal flow tanks, the main task is to achieve ideal condition, you can say equal velocity at all points, lying on each vertical line in the settling zone. And in the rectangular tanks, usually that flows longitudinally. Okay, they can also have scrapping devices to scrap the left out sludges. And in the circular tanks with radial flow, where we will be having the central feed, as we saw in the layout earlier, water will enter at the center of the tank and of the into a circular well provided with multiple ports from which it will go out to flow radially outwards in all direction equally, and the water will finally flow horizontally and radially from the center towards the periphery of the circular tank. The main aim here is to provide uniform radial flow with decreasing horizontal velocity towards the periphery, from where the water is withdrawn from the tank through the effluent structure, and the sludge is scrapped to the central sump mechanically and continuously from where it is withdrawn during the operations. This is my typical layout. Here you can see the water is flowing peripherally, or there is uniform velocity here. Okay, and there should be a decreasing horizontal velocity. You can see this is my influent, and the water is flowing peripherally. Then we have a decreasing velocity here, and then from here you will be getting the sludge out. Now we have certain formulas that we really need to take care in the case of the design of the sedimentation tank. So this is the overflow rate. We also call this OFR. It is equal to discharge on the surface area. Now the discharge is volume by time, and this is equal to surface area. If it is a rectangular, it will be L into B. If it is a circle, it will be pi by 4d square. Now if you simplify it more, it will be equal to the depth by time. Now there are three assumptions that is to be taken in case of horizontal sedimentation tank. The particles and their velocity vectors are evenly distributed across the tank section, and this is the function of the inlet zone, and the liquid will move as an ideal slug down the length of the tank. Any particle hitting the bottom of the tank is assumed to be removed. And if Q is the discharge entering the basin at which the water is flowing, so V is equal to, this is the velocity, is equal to Q upon BH, where Q is the flow rate and B is the width of the tank and H is depth of the water in the tank. Now let us solve a simple numerical, and there is one more formula, which is detention time, which is equal to dt is equal to volume of the tank upon the rate of flow, which is Q, or V is also is equal to Q into dt. And in certain special cases, the detention time for the circular tank is equal to d square 0.011d plus 0.785h multiplied upon Q, where h is the depth of the tank and d is the dia and Q is the flow rate, or h sometimes also we call as vertical depth at wall or side water depth. And there are certain assumptions, design criteria, where detention time is lying from 4 to 8 hours. For the plain sedimentation tank, you can say PST, and the width of the tank is usually 10 meter and not allowed to exceed, and it can be from 10 to 12 meters. If you're designing a tank or a sedimentation tank, you need to be sure that all your parameters are lying within these ranges, and the length of the tank is not allowed to exceed 4 times the width. And it can, and though it may vary from, it can vary from 1 to 6 times also in certain cases. The cross-sectional area of the sedimentation tank is such as to provide horizontal velocity should be from 0.15 to 0.9 meters per minute. So we can convert that subsequently into meters per second also. And the total amount of flow from the tank within 24 hours generally equals the maximum daily demand of the water. Now, if the currents on the other hand permit a substantial portion of the water to pass directly through the tank without being detained for the intended time, the flow is said to be short-circuited. Properly designed inlets and outlets near the entrance and exit may reduce the short-circuiting tendencies and distribute the flow more uniformly. Now, let us solve a simple numerical. Here, for example, we have been given here the maximum daily demand of the water purification plant has been 12 millions per day, and then we have to design the dimension of a suitable sedimentation tank fitted with mechanical sludge removal arrangements for the raw supplies, assuming any detention period here is 6 hours, and the flow, any velocity, horizontal flow is 20 centimeters per minute. So first of all, what we have to do, this flow is basically for 24 hours, 12 into the quantity of water to be treated for the time period of 6 hours is equal to 12, okay, into 6. So it would be 3 into 10 to the power 6 liters. And then we know that 1 meter cube is equal to 1000 liters. So it would be 3000 meters cube. So this is my capacity of the tank. Now we already in the question we know that the velocity of the flow is 0.2 it is 20 centimeters, so it will be 0.2 meters per minute. So the length of the tank required is equal to velocity of the flow into detention period, which is VH, it equals to 0.2 into 6 into 60, which is equal to 72 meters. So the area, surface area, would be 3000 meter cube. We already calculated that, upon 72, which is equal to 41.67. So this is in my range, this one, the length we got. Now if we assume the depth is equal to, suppose we are taking this as a 3.5 meters, so the width of the tank is equal to 41.67 upon 3.5, which is equal to 11.90. And then using a free board, so it will be equal to any, we can add the free board in depth. We have taken 3.5, and if we take 0.5 meter of depth, it will be equal to 4 meters. And then the overall size, the overall size is equal to 72 multiplied 11.9 multiplied 4. So this is my final dimension of the sedimentation tank that we are going to design. Subsequently, you can see other questions also if you're designing a circular tank or horizontal flow tank. Depending on the questions, you have to solve it considerably. This was all about the design of the sedimentation tank.